All right, hey AP Chemistry. We're going to be looking at the Unit 8 Important Information Part 1 notes, and we're going to actually jump all the way to the last page where we're going to discuss percent ionization. In the last set of problems that you did, we did do a percent ionization type of free response question. Now we're going to put some notes to that and see if it makes even more sense. So percent ionization corresponds to a weak acid because a strong acid's percent is 100%. So we don't have to worry about what percent for strong acids. We got 100% ionization with a strong acid, but for a weak acid, there's going to be a certain percentage. So we can quantify the ionization of a weak acid according to the percent of acid molecules that actually ionize. So if I have my acid that's aqueous, HA, and I add it to water, liquid, weakly equilibrium, H3O plus aqueous plus A minus aqueous. So the question becomes, how much of this H3O plus came off from my HA? If I know how much H3O plus and I divide it by my original HA and then times by 100, that's going to be my percent ionization, or also known as percent ionization is the concentration of the ionized acid, which is the H3O plus, over the initial concentration of acid, HA, times 100. So in sample problem 11, I'm going to jump over to there. If you look at sample problem number 11, when you have a weak acid and you have to solve for the concentration of H plus or H3O plus, you need to do an ice table. And so I had just posted a video on sample problem 11 in which we did that. And it looks like my concentration of H plus at equilibrium was approximately 9.6 times 10 to the minus third. If I turn this number into scientific notation, 1, 2, 3, 9.6 times 10 to the minus third molar. Okay, that's how much H plus broke off of the HNO2, or that's how much H plus ionized or dissociated from the HNO2. So if I want to calculate the percent ionization of the 0.2 molar HNO2, and don't forget in that question, it started with 0.2 molar HNO2. If I want the percent ionization, it's the concentration of the ionized acid. We know that it's 9.6 times 10 to the minus third molar H3O plus over the concentration of the regular whole acid, 0.2 molar times 100. So 0.2 molar of HNO2 times 100. And so I could take this and I'll do 9.6 times 10 raised to the minus third divided by 0.2 times 100, and I get 4.8% ionization for 0.2 molar HNO2. Okay? And so if I were to want to figure out the percent ionization, I would need the concentration of H3O plus, which is basically the value of X from the ice table, and then the initial concentration given to you. So this requires a couple of steps, and I'm going to do those couple of steps in sample problem number 16. So it says, find the percent ionization of 2.5 molar HNO2. So now I have a different concentration. I have 2.5 molar HNO2. So I'm going to calculate and use an ice table. Ka is 4.6 times 10 to the minus fourth. I'm going to write out my acid dissociation equation. And I'm going to use H plus instead of HA. Instead of having H3O plus, it's the same thing as saying concentration of H plus at equilibrium over concentration of HA initially times 100%. It's the same thing, all right? So I have HNO2, that's aqueous. If I want to write my acid dissociation equation, I'm going to have H plus. I know that comes off. And then I have NO2 remaining, and it's going to be NO2 minus. NO2 minus aqueous. And if you need help with writing acid dissociation equations, I'll have a video, but it's also written right here. Here's the generic equation. HA plus H2O is H2O plus and A minus, in which A minus is whatever is connected to the H in your acid. All right, so I have 2.5 molar HNO2, and its Ka is 4.6 times 10 to the minus fourth. So let me do an ice table to figure out how much H plus broke off. Okay, have too many lines, but it's okay. All right, so I, C, E. Okay, and so initially I have 2.5 molar HNO2 and no H plus and NO2 minus. This is exactly how you're going to calculate pH or H plus of a weak acid, right? And so we're not going to calculate pH for this problem, but this is what the same exact procedure and ice table that we've done in Unit 7 with equilibrium. So now my change, everything's a 1-to-1 mole ratio, so minus X. That number is going to be the same, plus X plus X. And so in the end, I got 2.5 minus X, X, and X. And so I could write my Ka expression. Ka is equal to H plus times NO2 minus all over HNO2. You can kind of see that I almost could get my Ka expression if I had my percent ionization, because the percent ionization is just this. And so we're going to look at that later. So now I'm going to solve. I'm going to plug this in. I'm going to get X times X, which is X squared, over 2.5 minus X equals 4.6 times 10 to the minus fourth. We're going to make that nice assumption because we don't want to use quadratics, and we're not going to worry about quadratics, and say that X is approximately equal to 0 because Ka is less than 1. If I solve for X, I'm going to do the math on the calculator. I'm going to take 2.5, multiply it, times 4.6 times 10 raised to the minus fourth. And then I'm going to take the square root of that. Okay, so second square root, second answer. And I get X is equal to 0.0339 molar. Right, because I know X is going to be my value of concentration of H plus and NO2 minus. Now I know my value of H plus at equilibrium, and if I want to calculate the percent ionization, I have to use this value of X, put it over my initial value of my acid, and times it by 100. So let's do that. Percent ionization is going to be concentration of H plus at equilibrium, which is X. That's just X. Over initial concentration of acid times 100%. So let's do this. 0.0339 molar over 2.5 molar times 100. Let's see what value we get. 0.0339 divided by 2.5 times 100. I get 1.36%. That's lower, right? Originally we had 4.8% dissociation, and that was with a lower concentration of HNO2. We had 0.2 molar, and a lower concentration gave me a greater percent ionization. Now I have a higher concentration, and I have a lower percentage. So we're going to simplify or summarize that with these two summarizing points here. And I put them at the bottom on purpose. The equilibrium concentration of H2O plus of a weak acid increases with increasing initial concentration. So look, it makes sense. If I have more HNO2, I'm going to have more H plus. And look at this. This value is definitely larger than this value. 0.0339 is the same as saying 3.4 times 10 to the minus second molar H plus. If I had 0.2 molar, I only get 9.6 times 10 to the minus third molar H3O plus. This number is smaller. So the amount of H3O plus is smaller because I have a smaller concentration. But the percent ionization decreases with increasing concentration of the acid. So the 2.5 molar only gave me a 1.36% ionization. The 0.2 molar gave me a 4.8% ionization. And you could prove this when you do your calculations like we just did, but keep in mind that if I had maybe a 5 molar solution, I'm probably going to have lower percentage ionization. And if I had maybe a 0.05 molar, I'm probably going to have a higher percent ionization. Sorry, I'm squishing that in at the bottom there. Okay, so this is the end of our Unit 8 notes with percent ionization. What I would like you to do now, and this will be given in our agenda document, and I'll be told to you, you're going to move on to doing some Chapter 18 exercises to make sure you understand these Unit 8 notes with the videos. For acid practice, you're going to be doing problems 64, 66B, 70, and 72. That's just 4 of them. Then for bases, which kind of switches it up and it does base dissociations, and something known as PKB, you're going to do problems 88, 89, 92, and 94. I will be providing a bit of support and help with these problems. The only thing that I will make a note of for this is something known as KA and KB, PKB and PKA. PKA is the negative log of Ka. PKB is the negative log of Kb. And just like pH, 10 raised to the negative pKa equals Ka. 10 raised to the negative pKb is Kb. And you are going to use these for your ice tables. One of the problems, I believe it's 92, I believe it's question 92, says, oh, the pKb is this number. If you take 10 raised to the negative pKb, it's going to be equal to Kb. All right, so I'm going to end this video here. You're going to be working on these Chapter 18 exercises at the conclusion of this video, and you'll have another day to work on those problems. And I'll be available in the Remind and in email and in the Google Classroom if any of you have any questions or concerns about these problems. And I'll try to make sure I post an answer key for these 8 problems on acids and bases.